Today we are going to discuss about the finite difference approximations to derivatives. Before that, a quick recollection of our previous class. In the previous class, we were discussing about finding the solution of partial differential equations through numerical methods and stated that the most popular numerical methods are the finite difference method FDM and the finite elements method FEM. Even though both methods can be used for most problems, a debate is going on about the superiority of these methods. Which is the superior one? FDM is found to be simpler to describe as well as to program. On the other hand, FEM is somehow deeper from the mathematical point of view and is more flexible when solving equations in complex geometries. We are concentrating on the FDM, the finite difference method. In FDM, we replace the derivatives occurring in the partial differential equations by means of their finite difference approximations, and then we solve the resulting linear system of equations by a standard procedure. To present the principle of the finite difference approximation, let us start with a two-dimensional problem. Consider a two-dimensional problem represented by a smooth function u in variables x and y. That is, the solution domain becomes the xy plane. And suppose that this plane be divided into irregular rectangular grids of width h and height k. The two-dimensional finite difference grid is shown here. The point of intersection are called mesh points or lattice points. Sometimes they are known as grid points or nodes. Conventionally, the values of u at these grid points are denoted by uij. In finite difference method, we replace these uij's that occur in the partial differential equation by their finite difference equivalents. Then we write the difference equation corresponding to each grid point using function values at the surrounding grid points. That is, uij is expressed in terms of ui minus 1 comma j, ui plus 1 comma j, and so on. Finally, solving these equations simultaneously gives the function at each grid point. Now let us look into the mathematics behind these equations. Using the Taylor series, we can expand u function of x plus h as u function of x plus h into first derivative of u plus h square by 2 into second derivative of u, and so on. Simplifying, we get u dash of x is equal to u of x plus h minus u of x divided by h plus o of h, where o of h is called as the truncation error. In this case, the truncation error is in the order of h. Representing u dash of x as ux, we will get the forward difference approximation. Similarly, we will get the backward difference approximation by expanding u function of x minus h in Taylor series. The intermediate steps are shown in this slide. A more accurate approximation, central difference approximation for ux, is also possible from the Taylor series as explained here. This is a second order approximation since the truncation error is in the order of h square. In a similar manner, it is possible to derive finite difference approximations to higher derivatives like uxx, uyy, and so on. Considering u function of xy as uij, we can rewrite the approximation equations for ux and uxx in terms of uij as shown here. Similar is the case with uy and uyy. After obtaining these finite difference approximations, we can replace the derivatives like ux, uy, uxx and uyy occurring in the partial differential equations and solve the resulting linear system of equations by direct or iterative methods. As a simple example, let us set up the finite difference analog of two-dimensional Laplace equation, and also let us discuss the method for finding its solution. Remember that the two-dimensional Laplace equation is uxx plus uyy equals 0. And we replace uxx and uyy with their finite difference analogs. Simplifying, we get the value of u at any point as the mean of its values at the 4 neighboring points. The last equation represents this. And this equation is known as the standard 5-point formula. Observe the figure shown here. This figure shown helps us to grasp the equation in a quicker way. We know that the Laplace equation remains invariant even after rotation of the coordinate axis through 45 degrees. The corresponding equation is the diagonal 5-point formula. It is evident from the figure why the name diagonal comes. Remember that the error in diagonal formula is 4 times that in the standard formula. Hence, in all computations, we usually prefer the standard 5-point formula whenever possible.